Okay, so in this example, we're talking about buffers. And what I told you guys is that on a pH titration curve, a buffer is sort of that area where there's not much change, okay? Now, think about a buffer like your stomach. So let's say, for example, you have like a pop, okay? If you have a sip of pop, your stomach's not gonna get upset. But because you're only putting a little bit of pop into your system. Let's say you have a cup of pop or a glass of pop. It's the same sort of thing, right? Like, it's not really upsetting your stomach. But let's say you just like hammer a pop, like you chug the whole thing, right? It's going to upset your stomach because your stomach is a buffer, right? It is maintained at a certain pH to combat certain things that you're ingesting, whether it's pop, whether it's food, whether it's alcohol, whatever, okay? So it's set to maintain the pH within your stomach, okay, for optimal conditions and environment. Now, if you hammer a pop, right, you're taking in so much, it's overriding that buffer, right? It's preventing it from doing its job. So when you add a ton of something, the buffer can't work. It doesn't work if you just add so much to override it. But if you just add a little bit at a time, the buffer is really good at just being like, hey, I'm gonna take that, react, and I'm good. That's why when we have a pH curve, let's take this one for example, this is your buffering region. Because if you add let's say this is an acid, and I'm adding in a little bit of base, the pH doesn't change for small amounts added. But once you've added a lot, the pH shoots up, okay? So that's a buffer. Now, a buffer is a conjugate system. That means it has a conjugate acid and a conjugate base. In this example, the buffer that we're talking about contains HF and F minus, okay? Now, calculate the pH for this buffer. So we have HF and we have F minus. So the first thing that we want to do is we want to understand that in order to calculate the pH, I need a concentration of hydronium. How am I going to get hydronium out of this situation? Okay, that's number one. Number two is a buffer contains a weak acid and a weak base in a conjugate system. And if both of the acid and the base are weak, then that means that we have an ice table situation, right? So that's what we're going to do. So we're going to say, okay, we start with HF, right? HF and F minus are the only two things we start with. If they're the only two things that we start with, what is there has to be something around them, right? And we obviously know it because both of these are aqueous. Yes, there's HF, yes, there's F minus, but because they're aqueous, they're water. There is water, sorry. So HF is gonna react with water, okay? And because this is a weak acid, we know it's gonna create an ice table situation where we have double arrows, partial ionization, creating F minus and H3O plus, which is what we want because we wanna find pH. Now, let's just talk about this, okay? If I have an ice table, okay, I have I, C, and E, right? But here's the thing. In this question, did it say that I have an initial concentration of HF or an initial concentration of F minus? No. All it said was that you have a buffer containing HF and F minus. The key point here, guys, is that if you have a buffer, you are at equilibrium. Okay, you have a buffer, you're at equilibrium. If you're at equilibrium, you can skip the I, you can skip the C, and you can go straight to the E. Because we're already at equilibrium because we have a buffer. Okay, now what that means is the concentration of HF is going to be at equilibrium 0.28. Water doesn't matter. F minus is 0.26, and I don't know what H3O is, but I need it. So we're going to give it a variable, we're going to give it X, okay? Now, because we have our equilibrium concentrations, just like anything else, we're going to set up our equilibrium law. So, I forgot to do it over here, guys, but this is a Ka expression. If I look at my data booklet, okay, for the HFKA, if I look, got it right there, 6.3 times 10 to the negative 4. So watch what's going to happen. When we write our equilibrium expression, or Ka expression, you're going to get 6.3 times 10 to the negative 4. That is equal to your products, which is 0.26 to the power of 1 times x, all divided by 0.28. Now, all we have to do in this question, ladies and gentlemen, is isolate for x. How do I do that? Well, multiply both sides by 0.28 and divide by 0.26. So multiply both sides by 0.28, divide by 0.26. And what that's going to give us for our x value is 0.00, do it in our calculator, another 0, 678, moles per liter, because we're talking about concentration of H3O. Now, because of that, I can calculate my pH. To find pH, which is the negative log H3O, which we just found using our equilibrium law. And according to this, our pH is going to be with, so I got 2 sig digs, so I need 2 decimal places. Round it out, put it in your calculator, it's gonna be 3.17. Now, I'm not gonna be here for your unit test, but if I was someone who was gonna be here for your unit test, this example would be very beneficial for you in preparing your unit exam.